Good morning, everyone. I can see there's still a few people actually connecting, so we'll just wait a second and let them get connected. And I'll just run through here and mute everyone's. Okay, looks like everyone's muted now. Okay, so let's get started. This will probably be a bit of a shorter lecture. We have 2 hours, but I can't see this really taking 2 hours. So we'll go through to the point where we finish this slide deck, and then we'll call it a day at that point. Before we get going, I believe we have a homework assignment due tonight. Anybody have any questions? Everyone managing to get through that okay? It doesn't look like we have any questions. So let's get going on today's lecture. I just need to share my screen here. And of course, I'm having trouble getting my available screens to show up. So just bear with me for one moment. Oh, this is certainly less than ideal because for whatever reason my screen sharing does not appear to be working. Can any of you guys see the slide deck? Yep. Okay. So at least I seem to be able to get that working. Okay. So this is actually the slide deck for week 6, and it deals with physical treatment technologies. Okay. The overview is we're going to take a look at contaminants in water, specifically what type of impurities we can have. Solids in wastewater, removal of solids from wastewater, removal of solids in air through scrubbers, types of separation to remove particulate matter from gases, and then we will talk a little bit about homework 3. Okay, so learning objectives to describe wastewater treatment processes for municipal wastewater and industrial wastewater. And to identify facilities that accept industrial waste for thermal treatment, recycling processes, or disposal. Okay, let me just see if I can get this onto. That's a bit better. Okay, so when you look at sources of water, I know the students who are environmental technology have probably looked at this quite extensively in some of their other environmental classes. I'm not so sure about the chemical engineering folk if you deal with this much in your program, but this slide takes us through some of the sources of water. And of course, the first one, groundwater through drilling of wells into aquifers. It's a primary source of drinking water. Porous consolidated rock or unconsolidated soil, wells and pumps used to remove water. So groundwater is a significant, as it says here, it's a primary source of drinking water. Where we are located along the north shores of Lake Ontario, we get our drinking water from Lake Ontario, but if you move away from the Great Lakes, you begin to get into areas. If you get down through Cambridge, Waterloo area. All of their drinking water comes from groundwater sources. In those areas, the groundwaters are covered through the drilling of wells, and those wells generally are drilled into porous consolidated rock or unconsolidated soils that have the hydraulic conductivity necessary to be able to pump great quantities of groundwater. I don't know if you guys have ever looked at the Ocala aquifer in the U.S. It's one of the largest groundwater aquifers in North America that's actually tapped for drinking and irrigating water. But if you have some time, maybe look that up on Google and take a look at it, and you'll learn about a little bit about groundwater aquifers. And in the case of the Ocala, how overuse of that aquifer has really resulted in some real water supply issues. Okay, so when we have these groundwater aquifers, these wells, they're typically installed to great depth. If you get out to the Cambridge area, I mean, these wells can be down, 100-200 feet into the main aquifer, but I mean they can also be shallow wells. But the one thing that is consistent between all these wells is that they all use pumps to remove that water. So the water is pumped from the aquifer usually into some type of storage reservoir. Surface waters, when we get to surface water, we have lakes, reservoirs, rivers. Rivers can be dammed to create reservoirs, and reservoirs store water during heavy rain, snow, and we also have the ocean as a source of surface water. I give the example of Lake Ontario. Lake Ontario is a major source of potable water for the Greater Toronto area. Especially those portions of it lying on the north shore of Lake Ontario. Reservoirs, there are some relatively large reservoirs. If you ever take a look at the Hoover Dam down in Nevada, the Hoover Dam is primarily built for the generation of electricity. But there is a very large reservoir that forms behind that dam, and that's a classic example of a river being dammed to create reservoirs. And of course, those reservoirs, they store water, during periods of heavy rain and snow. So a lot of these reservoirs, they get recharged. In the early spring when you get snow melt, and again in the fall when they get heavy rain. So the water is essentially stored there and is withdrawn from the reservoir as needed. And of course, the third example here is reclaimed wastewater. I can't think of off the top of my head any specific examples of reclaimed wastewater, but it is something that it has been done in some areas, and even in the industrial area. A lot of industrial facilities are looking at how can they reclaim their process water so that they can reuse it in their processes, as opposed to bringing fresh water in from the municipal system. Okay, so if you look at contaminants in water, we have suspended solids and particles. These can be aboard. Aaron had just pointed out that aboard ships, they typically reclaim their water, and I can see why they would want to do that, especially some of these larger cruise lines. Would make sense that they would attempt to reclaim any water that they use. Okay, when we get to the suspended solids and particles, typical suspended solids are sand, silt, precipitated salts, and other solid particles. These particles are there in different sizes, and mechanical processes such as filtration, settling, or separators are used to remove those solid contaminants from water. Other particles, even if they are not in solution, may not settle. And an example that's given there is colloids. These particles will need coagulation to form large particles, then filtrate and or settle. So I did give an example previously of industrial wastewater treatment plants, where once they make the all the dissolved solids, once they precipitate them, they're generally there in very, very small particles, typically colloids, and they need to add a coagulant or a flocculant to get those very fine particles to clump together to form larger particles, which can then be filtered and settled out of the water. If they don't do that coagulation and flocculation process, the particles just remain in the very fine form, and the majority of them will just pass through the system with the water. You also have the dissolved solids and salts, metallic and non-metallic compounds not separated by mechanical means, but by adding chemicals, causing precipitates as insoluble compounds. Okay, and that comes back to the last point, where many industrial facilities have dissolved solids in their wastewater, and they precipitate it. In the case of if it's metal, dissolved metals, they will precipitate them using metal hydroxide reaction, which converts the dissolved solids into insoluble materials, and which are then precipitated. You can also use membranes or heat to convert the dissolved solids into solid particles. Membrane technology, it is out there and is actively used. It's actually actively used in the industrial sector as well, because they will use membranes typically ultrafiltration membranes. So they're membranes with very, very small pore diameters. The wastewater are pumped into the membrane system. Water passes through the membranes, but the dissolved solids, because of their size, will be blocked by the membrane, and they remain on the dirty side for recovery. Okay, contaminants in water, dissolved gases, water exposed to air, nitrogen 80%, oxygen 18%, carbon dioxide 3%. In the atmosphere, 78.21 and 0.03% of those gases. Carbon dioxide forms carbonic acid when absorbed in water. So there's like a couple of questions coming up here. But can any of you guys think of any issue that we are hearing a bit about, and it relates to global warming and carbon dioxide forming carbonic acid? Any of you heard of any of the issues surrounding what the concern is with the formation of carbonic acid, particularly in ocean environments? Well, it doesn't look. Maybe one of you are going to take a stab at this. Acidification of the ocean, and that's it exactly, right? As carbon dioxide levels are increasing in the atmosphere, the amount of carbon dioxide in the atmosphere is slowly increasing, which is forming carbonic acid in the oceans. I did actually read one study a little while back that said that over the last 10, 20, 30 years, the pH of ocean water has dropped by 0.1% because of the formation of carbonic acid. And while 0.1% doesn't seem like a significant increase in the pH of water, because the pH scale is logarithmic, that really translates into a 30% increase of in the acidity of the ocean water. And of course, the big issue with increased acidity is that shell-forming organisms are losing their ability to form shells. Because these shell-forming organisms, they use carbonate ions to form their shells, and as carbonic acid is formed in the water, there is just significantly less carbonate ions available for that shell forming process. So that is a kind of I would say call it a secondary issue to the greenhouse gas issue, where the carbon dioxide in the atmosphere is resulting in increases in air temperature, also increases in the temperature of surface waters, at least the shallow to the shallow depths of surface waters. But we also have this issue with acidification of the ocean. So here's the next question then. So why does dissolved oxygen cause or contribute to corrosion? Any thoughts on why dissolved oxygen can cause or contribute to corrosion? Doesn't look like anybody's going to be willing to take a stab at this one. So oxygen results in corrosion through the oxidization of I'll use iron as an example, but it can also happen to other metals, aluminum being another example. But when you look at iron, oxygen will oxidize iron to ferric oxide. So when you see the red rust that's associated with a piece of metal that's been outside or exposed to the elements, what you're actually seeing is that iron oxide layer. The one important thing to note is if you have iron and oxygen in a 100% dry environment, you do not get corrosion. You need iron, oxygen, and water in order to get corrosion of iron. And the atmosphere contains enough water vapor to cause corrosion, but it becomes even more so of an issue when you're dealing when you're actually moving water that does contain dissolved oxygen within it. Many wastewater treatment plants struggle with corrosion of the piping systems within their plants. And there are many ways, many processes that they do to minimize the amount of corrosion that takes place. You can also have organic matter in water as a contaminant. And the organic matter, it's heavily embedded with carbon. So I mean, you can get naturally occurring organic matter. The runoff water that's been in contact with leaf litter will give you tannins, which will discolor discolor water. But you can get all kinds of organic matter as a contaminant in water, and some of it can be as a result of pollution instances where the organic matter can consist of organic substances like toluene, xylene. Organic molecules can be soluble. Stop my screen here. Can be soluble, such as pesticides and herbicides. Inorganic matter can be petroleum products and living organisms such as bacteria, viruses, algae, protozoa, and their remains. So as I say, I mean, I give you a couple of examples there. With toluene and xylene being organic contaminants. But as this mentions, I mean, you can have multitude of other ones, naturally forming or as a result of human activity. Okay, impurities in water, you can get dissolved impurities. You can the inorganic ones: calcium, manganese, chloride, nitrite. The organic, humic, fluvic acid, pesticides, detergents. So those are just some examples of dissolved impurities. When we look at calcium and magnesium, those type of contaminants are actually what participate in the hardness level of water, and hard water can actually be a significant issue for any type of treatment system, or even in residences that use groundwater as their drinking water source. Hard water, it can start plugging their pipes. It can be difficult to do laundry in hard water. And again, the organic ones, I've already given you a couple of examples of those. Suspended impurities, colloidal, which can be clays, and peats. They can be organic, industrial and domestic byproducts. Inorganic, which could be sand particles, and then of course you have your living matter, which is your microorganisms, bacteria, algae, and viruses, macroorganisms, fish, worms, and larvae. The living matter, when we come to the microorganisms, they are of course a significant issue, especially when it comes to drinking water supply, and it's important that potable water supplies be treated for the removal of bacteria or viruses. The classic example, and I'm pretty sure that all of you have heard about it, is the Walkerton crisis, where we did end up with E. coli bacteria in the municipalities potable water well. The treatment system wasn't working as it should have. The well itself was improperly designed, and that resulted in surface water runoff that had passed through farmers' fields where there was cows grazing in the fields. That surface water essentially flushed E. coli bacteria into the well, which was then pumped into the municipal distribution system. And I don't quite recall the exact number, but I believe that potentially up to 11 people may have actually died as a result of that issue. And because of Walkerton, that's why we have a lot of our regulations surrounding water supply and water treatment, and the training of water treatment plant operators. Prior to Walkerton, none of that existed. There was no need for any type of certified operator to work in these treatment facilities, and that was one of the big things that came out of the Walkerton crisis. Investigation was that the people that were operating the treatment plant essentially had very little training or background in the operation of a municipal water treatment facility. Okay. Great. Solids in wastewater. Solids typically include inorganic matter such as silt, sand, gravel, and clay, and organic matter such as plant fibers and microorganisms from natural and man-made sources. They're generally classified by their size and their state, their chemical characteristics, and size distribution. Solids can be dispersed in suspended and dissolved forms. So that's a key point to kind of take note of, is that these solids can be present as suspended solids or as dissolved solids. The suspended solids are generally speaking easier to remove from water. You can pass water through various filtration systems, which will remove those suspended solids. But the dissolved solids, they can be a bit harder to remove, because they usually involve some type of reaction to to convert these to suspended solids so that they can then be removed. Based on size, solids and water can be classified as suspended, settleable, colloidal, or dissolved. Volatile, absorbed, none, or non-volatile. So those are just really the different classifications of these solids. Suspended solids. If you take a jar and you add some soil to it and you shake it, the settleable solids will drop to the bottom of that jar within minutes of you stopping agitating it. The suspended solids, they will typically slowly settle out, but the colloidal or the dissolve, they can take a very long time to settle, and in some cases will not settle at all, especially when you're talking about dissolved solids. Okay, so they have this video that is embedded here, and I've just lost my mouse, so let me just so I can see I can get my mouse back. So hopefully, unfortunately, we have to watch this. Okay, so we'll watch this. So we should be back onto the slides now. If you guys can't see if you can't see the slides, maybe just somebody let me know. But that was just a short video that runs through the primary treatment of water treatment systems. And as you can see from the video, the primary treatment it's essentially all physical processes designed to reduce the solid content of the water and to start the process of reducing the BOD. How familiar are you guys with BOD? Is that a term that you guys are familiar with? Anybody? Doesn't sound like too many of you are familiar with BOD, but of course BOD stands for biological oxygen demand. It is something that is actually monitored in industrial wastewater discharges. Your biological oxygen demand needs to be below a set limit. I believe in most municipalities it's around 150 milligrams per liter. But essentially the BOD is it's somewhat of a surrogate measure for the amount of organic materials in your water that can be easily broken down by bacteria. I don't know if you guys still do it, but I recall when back in the day when I was at Durham College, we actually used to do an in-lab BOD experiment where we would measure the biological oxygen demand of various waters. So maybe it's something you guys have done already, or maybe it's something that will be coming up in the final year of your program. But it is a parameter that causes us lots of grief when we're dealing with industrial wastewater treatment facilities, because it is a parameter that is very difficult for the typical industrial wastewater treatment system to remove the BOD content. So it is problematic for facilities that end up exceeding their BOD limit. Okay, so we'll continue on. Removal of solids for wastewater. Coarse and fine material separation utilizing screens and strainers. So this further removal of the typically the coarse, as it says there, coarse and fine particle sizes. It's a mechanical process. Use of coarse or fine screens are used to remove solid contaminants from wastewater, such as hair, paper, labels, plastic residuals, and production residues, etc. So if you ever go into either a municipal or an industrial wastewater treatment plant, one of the first things you will see in there is generally some type of screen, and the incoming water is passed through that screen, and any coarse materials that is in the wastewater will be removed, because you don't want coarse particles like hair and paper, plastic residues moving through your system. It will just cause problems. So the first step is the removal of the larger sized solids through these screen separators. Filtration separates solid substances from fluids. Mixture passes through a filter, as I described there. One of the first things you will typically see is a large screen that removes the larger portions, removes organic and inorganic suspended solids, sands, and dust from wastewater, drain sludge and filter presses. So filter presses are something that you generally will not see in a municipal wastewater treatment plant, but the vast majority of industrial water treatment plants contain a filter press. Once the solids are removed from the water, they typically pass through a clarifier, and those solids are pumped from the bottom of the clarifier to a filter press, which compresses the solids into a cake-like material and reduces the water content of it, so that it can be more easily handled for shipment off-site as either a waste product from industrial plants or from municipal wastewater treatment plants. It is usually used as an amendment on farmers' fields. Okay. Used for the purification of surface waters to provide domestic and potable water. So, I mean, filtration is one of the key steps for the purification of surface water. Quite often they use large sand filters, but the incoming water is passed through these filters, and it removes the majority of the suspended material that is in that water. Okay, membrane filtration separates and concentrates dissolved and undissolved substances under pressure from wastewater. Due to its specific pore size, the membrane retains particles and molecules of a certain size. So the key there, excuse me, the key there is that depending on the pore size of the membrane, these membrane filtration systems can be designed so that they're not only removing suspended solids, but they are also removing large molecular size dissolved solids. Microfiltration separates particles, bacteria, and yeast. Application and cold sterilization for the separation of oil, water, emulsions. I think I spoke briefly, I think it was in the last class, or where I spoke briefly about emulsified oils and how emulsified oils can be very problematic because they are difficult to remove from wastewater, because they essentially become suspended in the column of the wastewater. Microfiltration systems are out there for the removal of these oil water emulsions from water prior to discharge, and we see them commonly in industrial facilities that generate large amounts of oily water. And part of the problem in industrial facilities when they generate these oily water wastes is it's usually being pumped, and it's usually passing through process equipment, which tends to agitate the oil water mix, which in turn results in emulsions. And once those emulsions are formed, they are very difficult to remove from your wastewater. Ultrafiltration separates particles, microorganisms, proteins, and turbidities from the water. So ultrafiltration systems are quite often excuse me, used in generally small scale water supply systems. They will use ultrafiltration to remove microorganisms and proteins. Nanofiltration, application for viruses, heavy metal ions, large molecules, and very fine particles, used for water softening and the treatment of potable water. So you can see that you have various steps of membrane filtration, from micro, ultra, and nanofiltration. Each one of those systems target solids of various sizes. Reverse osmosis application, commonly found to desalinate seawater and decalcify boiler water in power plants. There are many countries, especially over in the Arabian Peninsula area, that their main source of drinking water is from the oceans and seas that their countries border. And of course, you cannot just take seawater and use it as a potable water supply. So they use reverse osmosis as a process to remove the salts and to create potable water from seawater. And it is probably a process that we're going to see significantly more of as we run into issues with water supply like they're seeing in the western portion of the United States right now. And as it says here, reverse osmosis systems are also used to decalcify boiler water in power plants. The decalcification of boiler water is a fairly important step. If decalcification was not occurring, the calcium ions they can come out of solution and begin to plug up tubes in the boiler system. So reverse osmosis is commonly used in power plants. When you get down into smaller scale boilers that you typically see in industrial plants, they're generally using chemical processes to reduce the calcium level of their water. Reverse osmosis concentrates dissolved substances by applying pressure through a semi-permeable membrane that reverses the process of osmosis. When applied pressure is higher than the respective osmotic pressure, the molecules of the solvent diffuse to the side of the membrane where the dissolved substance is already less concentrated. So the pressure of these reverse osmosis systems is critical for the operation of them. Flotation removes the dispersed or suspended substances from fluids by means of very fine gas bubbles that transport the substance to the surface. Substances are removed with a clearing device, applies to separated oils, fat, and finally suspended solids and particles. Sedimentation uses gravity to separate solid particles in sedimentation tanks based on density. Dense solid particles settle on the bottom of the tank. The sedimentation tank is a flat, nearly current-free tank, specifically designed for sedimentation processes. So usually when tanks are used for the sedimentation, they're usually very large structures. And the reason for that is because you essentially need to have a close to laminar flow through these tanks so that the particles will actually settle. If you don't have a current-free or nearly current-free tank, the current would just result in maintaining those solids suspended within the water column. Okay, it's 9 o'clock. Let's take a 10-minute break, and we will come back at the next slide. Okay. All right. Thanks, guys. Okay, so it's 10 after 9. Let's get started and get through these slides. It's actually taken me quite a bit longer than I anticipated to get through this. So let's continue. Municipal water supply and wastewater treatment. Essentially, a municipal water supply includes the intake. The intake is essentially can be either a well into a groundwater aquifer, or it can be a pipe that is out into a surface body like a river or a lake. If you look at Durham Region's intake for the Duffins Creek water supply plant, that intake is out. I believe it's almost a kilometer out in the lake, and you want those intakes to be somewhat away from the shore because the quality of the water is generally better when you're not pulling your water directly from the shoreline. So the intake is the first part. Once it's into the plant, you have this disinfection process that can be physical through either UV radiation, heat, or membrane filters, or it can be chemical disinfection using chlorine, ozone, chlorine dioxide, iodine, or other antimicrobial chemicals. The only wastewater treatment facility that I've actually spent a great deal of time in is the Durham Region treatment plant in Ajax, and they use a chlorine dioxide disinfection system for the reduction of microbial constituents. After disinfection, you have filtration, rapid granular media, slow sand, and other biological filters, or it can be membrane filters, micro, ultra, nano, and reverse osmosis. Rapid granular media, an example of a rapid granular media would be something like carbon vessels. Slow sand and other biological filters, sand filters are significantly finer material than granular media, so they're usually referred to as sand trickling filters, where the water is distributed on the surface of the sand filter, and as it percolates through the sand material, the solids are removed, and then potentially could be membrane filters, as we discussed in one of the previous slides, which can be micro, ultra, nano, or reverse osmosis. Other physical chemical removal processes can be chemical coagulation, precipitation, and complexation, adsorption, for example, activated carbon, bone char, or ion exchange, synthetic ion exchange resins, zeolites, etc. So after the filtration process, I want to say most water treatment facilities then have a chemical coagulation process where they usually add a substance like alum to the water, and the alum results in the coagulation of fine suspended materials, which can then be settled. And adsorption, as it says there, activated carbon. Activated carbon is good for the removal of organic compounds. Some activated carbons, specialized activated carbons, can be used for the removal of some metals, but they're usually used to target organic materials that are in the water. And of course, ion exchange. I keep pointing to the example of your lab where you have deionized water in the lab because of it passes through an ion exchange system consisting of typically several resin beds, which remove suspended solids through the exchange process. Okay, and then storage. After the water has been through the treatment system, it goes into some type of storage system where the water is accumulated for use by downstream users. If you look at especially where we are in southern Durham region, our reservoirs are typically in-ground reservoirs. The water is pumped from the treatment plants to these reservoirs, and then it's distributed from use from there. The storage is required so that fluctuations in the rate of use of the water can be accommodated. If you didn't have storage, you could end up with issues of supplying enough water to the system, especially during high demand time periods. When you get away from the southern parts of Durham region, you get up into the northern parts, many systems that are using groundwater wells for the water supply, they use above ground tanks. And you can see them as you're driving along to the side of the highway. They could either look like just very large above ground storage tanks, or they can be large suspended tanks that are put many feet up into the air, and water is pumped into these above ground storage tanks. And then from there, it drops from the storage tank to the supply system. All right. So this is what water treatment schematic looks like. You have wastewater effluent, and we saw this. We saw this in the video that we watched, where we have the preliminary treatment and the preliminary treatment and the primary treatment. Those are generally physical processes that remove suspended solids, and the suspended solids from those primary treatment systems, they end up going to sludge treatment for sludge treatment and final disposal. And as I mentioned in the video, these sludges can be high in nitrogen and high in phosphorus content. So they are, wherever possible, used for distribution on agricultural fields, so that that nitrogen and phosphorus content can be reused, essentially reused for the growing of crops. Once you're through the primary treatment, you're now into the secondary. That's where you're into more of the chemical type treatment processes, and you do get solids removed from the secondary process again. And again, that goes to sludge treatment and disposal. And after secondary treatment is where you will typically see disinfection of the water through typically the injection of chlorine into the water. Not all plants have a tertiary treatment systems, but some do. Once it's through the tertiary system, it is then typically discharged to some other water body. I was just looking at a chat that popped up there. So this is essentially a schematic of what we saw in the video that we just watched. The video focused on the primary portion of the treatment system. It didn't look at the secondary or the tertiary treatment at all. Preliminary treatment is a physical process that removes large contaminants. It captures large objects, and they have as examples here motorcycles, bodies, branches, with a series of screens. I don't know that a motorcycle would actually make it to a wastewater treatment plant. I doubt very much if a body would. But I mean, it's possible for small branches and sticks to make it there. And as I had mentioned, that type of material is used by a series of screens that is at the very start of the process, so that those large particles are removed prior to the water entering the primary treatment process. Primary treatment involves physical sedimentation of particulates. It occurs in a holding tank. It removes solid materials by sedimentation and by skimming precipitates from the surface. Calcium hydroxide and aluminum sulfate are used to form aluminum hydroxide, which sticks to particles in the water. This is the primary treatment was the focus of that video that we just watched, and is used for the physical sedimentation of those particulates. Secondary treatment involves the physical and biological treatment to reduce organic load of wastewater, uses natural bacteria to feed on organic matter in the sewage, convert it to carbon dioxide, water, and nitrogen compounds. So the secondary treatment, we talked briefly about BOD, the biological oxygen demand. The secondary treatment, well, it does remove some additional suspended and dissolved solids. It is this part of the process that will significantly reduce the biological oxygen demand of wastewater, and the reduction of biological oxygen demand is important, because if you discharge wastewater with a high BOD content to a surface water body, it can be very damaging to any type of life forms that are in the water, because the bacteria will use the available oxygen to start breaking down these organic materials, and then that available oxygen is no longer available to other life forms, and you can have things like large scale fish die off because of oxygen deficiency in the water. So it is important that BOD is removed, and this is part of the reason why BOD is regulated by municipalities for industrial wastewater treatment facilities. The municipal plants, they have a municipal treatment plants. I just looked at a chat there and lost my train of thought. Yeah, so municipal treatment plants, they're hard pressed to remove the biological oxygen demand from normal sewage without receiving wastewater from industrial facilities that is very high in BOD, which would also require removal at the wastewater treatment plant. So that's why municipalities regulate BOD and effluent discharge. And of course, tertiary or advanced treatments, this usual chemical precipitation of nitrogen and phosphorus containing an organic compounds. And for similar reasons why you want to reduce BOD content of effluent that is discharged, you also want to reduce nitrogen and phosphorus levels to as low as possible, because if you discharge wastewater that is high in nitrogen and phosphorus, you can end up with eutrophication of the surface water body and large scale algae problems. The Duffins Creek wastewater treatment facility, they are blamed. I don't know if it's actually the case or not, but they are blamed for being the source of significant algae problems that occur along the shores of Ajax and Whidbey every summer. And many people believe it is because of the amount of phosphorus that's being discharged from that wastewater treatment facility. Okay, and this is essentially a diagram showing the primary the secondary treatment process. And it's very similar to what we saw in the video. So I don't know that we need to spend a whole bunch of time on it. We looked at the primary process in fairly good detail in that video. But if you look at the secondary, you have essentially, an aeration tank in this example, and the aeration tank, an air pump provides air to that aeration tank, and the passage of these fine bubbles moving through the water column will begin the process of removing materials from the water. It goes into a settling tank where solids sink to the bottom, and scum will float to the top, and then into the chlorine disinfection tank to kill bacteria, and then discharge to rivers, lakes, or ocean. And the killing of bacteria is also an important step, because especially if you're discharged into a river, you can be discharged into a river where potentially there are potable water intakes downstream. So you want to make sure that the discharged water has been treated for the removal of bacteria before it enters that surface water body. So you all at the bottom here, you have the sludge digester, the sludge drying bed, and then of course the final disposal of the sludge to landfill or ocean, or applied to cropland, pasture, or rangeland. So wastewater treatment plants, municipal wastewater treatment plants, they generate a significant portion of sludge. If they have to dispose of that sludge to landfill, there are significant costs associated with that. So this is a big part of the reason why we have municipal sewer use discharge bylaws, so that they can regulate the amount of heavy metals that are coming into their wastewater treatment plants, because prior to disposing of the sludge to croplands, the sludge must pass chemical testing and must contain low levels of heavy metals. So heavy metals will tend to settle out in the process that are carried out at the treatment plants, and those heavy metals will become associated with the sludge. So the municipalities, they try to control that through the municipal sewer use bylaws to minimize the amount of heavy metal loading to their plants. And with my clients, the majority of court cases we've been involved in for breaches of the sewer use bylaw is because of the discharge of heavy metals to the sewer system. Because the municipalities, they really need to minimize the concentrations of heavy metals at their inlets. This is essentially just a flow chart showing the same thing as we saw in the previous slide. You can maybe gives a little bit more detail, but you can maybe take a look at that on your own time. Chemical coagulation and flocculation removes suspended particulate and colloidal substances from water, including microorganisms. Coagulation, that is essentially colloidal destabilization. In water treatment facilities, they will typically add alum, which is aluminum sulfate, or ferric chloride or sulfate to the water with rapid mixing and controlled pH conditions, and that results in the coagulation of those very small colloidal substances. Insoluble aluminum or ferric hydroxide and aluminum or iron hydroxide complexes form. The example that I give, and I've given this a couple of times, is when we look at the industrial wastewater treatment processes, facilities that are discharging materials like nickel, chromium, copper, they will use a metal hydroxide precipitation process. And in those processes, we get things like chromium hydroxide, nickel hydroxide, copper hydroxide form, and those forms are insoluble and will settle out. These complexes entrap and absorb suspended particulate and colloidal material. And of course, once they're entrapped and absorbed, they're able to be removed through settling or filtration. Flocculation, slow mixing, flocculation that provides for a period of time to promote the aggregation and growth of the insoluble particles, which is commonly called flocks. You can see at the start here it says slow mixing. I don't know if you guys have done much wastewater treatment stuff in any of your other courses, but when you're undertaking flocculation, you need to undertake it using slow mixing. If the mixing rate is too fast, you can end up shearing your flock, and essentially what that does is it takes those large flocks and shears them into smaller particles, and those smaller particles will pass through the wastewater treatment system. The particles collide, stick together, and grow larger. The resulting large flock particles are subsequently removed by gravity sedimentation or direct filtration. Smaller flock particles are too small to settle, and they're removed by filtration. So once you have those large flocks generated, they can be settled out of the water by, as it says just here, through gravity sedimentation. They can be passed through some type of filtration media, or as in the case with industrial wastewater treatment facilities, where the space is a premium, they will use what's called lamella clarifiers. These are just clarifiers that have inclined plates in them. As the water is pumped up against those inclined plates, the flock will impinge on the plates and will float to the bottom of the clarifier. And a good system, the clarification process is sufficient to remove your solids to levels where you can easily meet your sewer discharge bylaw limits. In cases where you can't because of residual smaller flock, you will have to go to some form of direct filtration. And facilities I deal with will use sand filters. In some cases, they will use bag filters or string filters to carry out that direct filtration. Okay. Microbe reductions by chemical coagulation and flocculation. Considerable reductions of enteric microbe concentrations. Reductions in laboratory and pilot scale studies indicate 99% reduction using alum or ferric salts as coagulants. Some studies report much lower removal facilities, so less than 90%. Conflicting information may be related to process control, coagulate concentration, pH, and mixing speed during flocculation. So, I mean, this is part of the reason why we have chlorination systems for the removal of microbes, because well, yes, you do have some efficiency in the removal of bacteria and viruses through coagulation and flocculation. These bench scale studies, as they indicate, it's not 100%. And you do need to be cautious about the presence of microbes in your effluent discharge. Expected microbe reductions of 90 to 99% if critical process variables are adequately controlled. No microbe inactivation by alum or iron coagulation. Infectious microbes remain in the chemical flock. The flock is removed by settling and or filtration. Must be properly managed to prevent pathogen exposure. That's usually accomplished by recycling back through the recycling back through the plant is undesirable in those in that situation, and filter backwash must be disinfected and disposed of properly. And of course, the disinfection process is designed for the removal of these pathogens. Okay, disinfection, any process to destroy or prevent the growth of microbes intended to inactivate, destroy the infectivity of the microbes by physical, chemical, or biological processes. Inactivation is achieved by altering or destroying essential structures or functions within the microbe. Inactivation process include denaturization of proteins, nucleic acids, or lipids. So those are just the various inactivation processes that take place. It can those processes can target proteins or DNA or RNA of the microbes, or they can target the lipid membranes or other lipids of the cellular structure of the microbes. Okay, so disinfection, excuse me, a very important process to ensure that microbes are inactivated prior to discharge of effluent. Properties of an ideal disinfectant: it's broad spectrum, active against all microbes. So, I mean, essentially, that's the definition of a broad spectrum. You wouldn't want to use a narrow spectrum disinfectant, say a disinfectant that only targets one type of microbe. You certainly want to use a broad spectrum so that it is effective against the wide variety of microbes that could be present in effluent. You want it to be fast acting, so it produces rapid inactivation. You want that inactivation to occur as quickly as possible in the process. It needs to be effective in the presence of organic matter, suspended soils, and other matrix or sample constituents. So that is a key consideration. You will have in wastewater treatment systems, you will have a chlorine demand that is there from organic matter. So you have to make sure that you are adding your chlorine or your disinfectant at a rate greater than the demand of the water that's being treated. It has to be non-toxical, soluble, non-flammable, non-explosive. I shouldn't say it must be. Ideally, it will be non-toxic, soluble, non-flammable, and non-explosive. Compatible with various materials and surfaces. Stable or persistent for the intended exposure period, and that's where your disinfectant demand comes in. You need your disinfectant to persist long enough to be effective against all the microbes that are present, and to provide a residual. Sometimes this is undesirable. There are cases where you don't want a residual, or at least not a significant residual. When we're talking about potable water supply, disinfectants are added to the potable water supply with a residual that the residual amount is designed so that by the time the water reaches the furthest point of the distribution system, there will still be some remaining chlorine in the water to work against the inactivation of microbes. But you can also have too high of a residual, and then you can get odors and taste associated with water. And of course, you wouldn't want to discharge treated water to a surface water body with too high a chlorine content because of its impact on the native biota. You want it to be easy to generate and apply, and of course you want that disinfectant to be economical. Okay. So a summary of the properties of water disinfectants: free chlorine, that's your hypochlorous acid and hypochlorite ion. Hypochlorous acid at low and pH, and hypochlorite ion at high pH. Hypochlorous acid is more potent germicide than the hypochlorite ion. It's a strong oxidant. It's relatively stable in water and provides a disinfectant residual. So you can add chlorine to water, and you can fairly easily achieve the required residual. Chloramines, mostly ammonium chlorides. It's a weak oxidant, provides a stable residual. Ozone's a strong oxidant, but provides no residual. It's too volatile and reactive. So ozonation systems, where they are used, are typically used very close to the point of use of the water, so that there's no time for microbial growth to take place between the point of treatment and the point of use. Chlorine dioxide, it's a strong oxidant. It's unstable in dissolved gas form. Concerns due to health risks of chemical disinfectants and their byproducts, especially free chlorine and its DBPs. The chlorine dioxide, as it mentions there, it is a strong oxidant and it is unstable. It is commonly used though at water treatment facilities, and I would suspect that that's due to the economics around using it. And of course, we constantly, I maybe shouldn't say constantly, but we often hear concerns about what are the health risks of chemical disinfectant. So what is the health risk associated with the free chlorine that remains in your drinking water as the residual? And some people will actually install systems to remove free chlorine from their water before they actually drink it because of those concerns. Okay, UV radiation. Low pressure mercury lamp, low intensity, monochromatic at 254 nanometers. You can have medium pressure mercury lamp, higher intensity, polychromatic, 220 to 280 nanometers, reacts primarily with nucleic acids, pyrimidine dimers, and other alterations. UV systems are very common with small scale groundwater source potable water supply systems. Many people will put a UV system directly in their home immediately after the supply point of the water, so that the water has to pass through the mercury lamp prior to being used within the house. Boiling, efficient kill, no residual protection, fuel and environmental costs. So we could always boil water to kill bacteria. Boiling is quite efficient at killing and removal of microbes, but it gives you no residual protection. You can boil water, and if that water remains standing for a period of time, you could have bacteria be reintroduced into the water before the point of use. And of course, you also have the fuel and the environmental costs associated with boiling water. That was something that I discussed briefly in a previous lecture where I talked about evaporation systems and the costs associated with operating an evaporator unit. Right. Tertiary treatment, nitrification, denitrification processes to remove nitrogen and phosphorus can involve filtration, carbon absorption, or constructed man-made wetlands. So nitrogen and phosphorus, they're a big issue when they get into natural waterways because of the eutrophication that it creates. As a point of interest, you might want to just do a Google Earth search for Lake Erie, and if the Google Earth image is taken in during the summer, you can actually see the algae in Lake Erie, because the lake is green with algae, especially in the western portions of the lake, and a significant part of the cause of the algae problem there is the presence of nitrogen, phosphorus, and runoff from the agricultural fields that are present in the watershed of Lake Erie, but also especially when you get down into the western portions of Lake Erie, there are some fairly major water treatment facilities that discharge to Lake Erie. So if you want to look at something interesting, go take a look at a Google image of Lake Erie, or just Google Lake Erie and algae, and you will come up with numerous documents and reports on that issue. Okay, so this slide deals primarily with the assignment that I think I have said is going to be due on October the 18th. I still have some work to do on this assignment, so I will get some additional information out to you guys in the coming days about the form of this assignment and what is going to be required. As I say, I will more than likely post an announcement when the assignment details are ready. Okay, and for the last slide, here are some references that you might want to go take a look at. Now I just want to do something just before we, just bear with me. Just before we all before we take off, we may need to have. Do we need our lab coats this afternoon and eye protection? You know, we did it. We did it last week without lab coats and eye protection. We did get permission to do that. So I would say, because we're going to go directly out to the into the field once we're done, that I don't think it's necessary to wear your lab coats. When you're in the lab, you can sit on the lab chairs, but try not to touch the benches as much as possible. Okay, so yeah, I will see you guys. At noon for that lab. Before we go, is there anyone that has is there anybody that wants to discuss anything with respect to the upcoming assignment or any other matter before we go? No, nothing. Okay, stick your hand up if there's anything you would like to discuss. Okay, all right. We'll end it. We'll end it here. Okay, all right. And for those of us that's in the lab group, I will see you at 10 after 12. Okay, thank you very much for attending. Bye now.